Well, good evening, everyone, and welcome. Thank you very much for coming out to hear about geology in the San Juans. It's absolutely a fascinating topic. I'm Ranger Jeff, Lead Interpretive Ranger at San Juan Island National Historical Park. And although we are a historical park, I get to talk about lots of cool stuff, and this is my favorite. Although I do have a tree walk, if you guys come to the island, it's pretty interesting as well, talking about how trees communicate. It's pretty darn cool. So a little bit about me. This is my second career. I was in a totally different line of work until about 7 years ago, and then I came west and started working in Yosemite as a ranger, and then Yellowstone as a ranger, and then here as a ranger, so pretty fortunate guy. In each of those places, I've been drawn to geology, an absolutely fascinating topic. Who can tell me what geology is? Anybody have a definition for me? Pardon me? Good one. So geology is how the earth changes, right? Changes in the earth. That's what we're talking about. We are talking about rocks, that's the primary component, but geology is really about how the earth evolves and changes. Thanks very much to Shannon for inviting me out. I appreciate it. And thanks to the library for inviting us as well. Thanks to my superintendent for allowing me to come over, and she was excited about it, so an opportunity for us to spread the word. So I'm pleased to be here. So what you see here is called an unconformity. This is found in southern Scotland, on the Atlantic coast of southern Scotland, or excuse me, the North Sea coast of southern Scotland. Anything you see here is multiple periods of history. So this was found by the gentleman that actually found this unconformity, and actually is the father of modern day geology. He found this in 1788. His name was Charles Hutton. And what he is seeing here perplexed him. He could not explain it. No one that he knew could explain it. What we have is rocks of an earlier period underneath rocks of the later period. There's no explanation for that in geology before 1788. So he began asking questions. How did this happen? How did these later rocks get underneath the much earlier rocks? And that's really where all of this started. If you've heard of this thing called continental drift or plate tectonics, you will know that we're talking about expanses of time that are hard to imagine. So what geologists have done to try and explain this is take the 3.6 billion years of Earth's history, cooled, right? It's really 4.6 billion years old, but 3.6 billion years when it actually cooled and things actually started happening on the planet. If we took that 3.6 billion years and we laid it out on a calendar of 365 days, you begin to understand how vast the expanses of time that we're talking about. Prokaryotes, the first life on the planet, right? This first life on the planet was originally eating chemicals and acids at the bottom of the sea. Eventually it became bacteria that was releasing oxygen. That was on February 25th of that year. On March 5th, the rock actually hardens on the planet. The first single-cell organisms in July, so we're over halfway through the year, and single-cell organisms without a nucleus are starting to show up. Dinosaurs, seems like forever ago, right? December the 13th. Flowering plants on December the 22nd. Primates, our ancestors, December the 28th. Modern humans, the last day of the year at 11:48 p.m. in the evening. You and I showed up at 0.005 seconds before midnight. So you're starting to get an idea of the expanses of time that we're talking about. How important, how big do you feel now, right? So let's get some terminology out of the way. Plate tectonics, you've probably heard about that in high school or college. Essentially, the crust of the Earth is floating around on liquid that's deep underneath it, and it floats around in these things called plates. And these plates touch one another, and sometimes they interact with one another. Terranes are fragments of those plates. So as these plates move and subduct and do other things, we'll talk about all of that, these terranes are just on the leading edge of that. Sometimes we call them exotic terranes because nothing around them is similar. That plays big in the San Juan Islands. Accretion, think of accretion as if we have one plate diving underneath another, and I'll get into more detail about these. And there will be tests at the end, by the way. As one plate dives underneath another, some of the rock is not heavy enough to subduct. It ends up getting scraped off. That's called accretion. Almost everything from the Rocky Mountains to the west coast of North America is accreted landmass. In other words, it started out somewhere in the Pacific Ocean, most likely as far away as 6,000 miles away, and how it got here is pretty amazing. Subduction is when one plate, usually the oceanic plate, slides underneath another one. The oceanic plate is covered by water because the rock underneath it is much heavier, right? And the one above water is much lighter. So when they touch, that landmass underwater wants to dive, right? It has to do something. It has to either strike and rise, it has to strike and slip, or it has to strike and subduct. All kinds of things happen at that interaction. A subduction zone is where two plates meet. And guess what? One of the most active plate boundaries on the planet is right over there, right? It's called the Cascadia subduction zone back here, but the Juan de Fuca plate just off 100 miles off the coast here is really driving all of our geology here. Faults is just fractures in that Earth's crust, breaks in it. We have multiple kinds of fault lines. Magma is nothing more than lava that hadn't reached the surface yet. Lava, molten rock that's reached the surface. And these plutons are big bubbles of magma deep underground. And they do lots of different things. Sometimes they rise and they push up things on top of it and make mountains. Sometimes they rise and they break the surface and they come up as volcanoes. So lots of things happening. So basic terminology out of the way, right? So this is, I can't run the subduction video because we're not attached, but it's fine, it's no problem. This gives you an idea of what subduction is all about. You see here, this mid-oceanic ridge. People ask, what is driving the subduction? How are these plates moving, right? There's actually, this magma is flowing underneath the plate boundaries. And as it flows, it pushes and pulls. We know that continental drift is caused by these things called mid-ocean ridges. There's one in the middle of the Atlantic Ocean that's driving all the activity in North America, and there's another one on the far side of the Pacific driving activity on the Pacific plate. What happens is there's a crack forms in the Earth's surface, a really big one, and magma starts coming up, and as it comes up, it creates incredible pressure. So what's actually happening is it's pushing those two plates apart. In the case of the Pacific, it's doing the same thing from the other direction. So you have the North American plate moving south-southwest at about 1 inch per year, and the Pacific plate moving north-northeast at about 1.4 inches per year. So that combined collision of 2¼ inches per year. So when that plate dives, we have subduction. Lots of things happen at subduction. I'll get into those. But you can see it's driving everything that's happening here, from the Cascade Mountains to the Olympics to the volcanoes and this thing called the Cascadia Arc, right, that runs all the way from Northern California all the way into southern British Columbia. That's what is driving everything that I'm about to talk about: subduction, accretion, and everything in between. So accretion, terrain building, is nothing more than the skimming off of material. Think of it as you take a warm knife over a stick of butter and it kind of peels up. Well, that's what's happening when these plates collide. Some of it is heavy enough to dive, some of it is not. What's not heavy enough to dive gets peeled off, and it becomes part of whatever it strikes, in this case, North America. I told you earlier that almost everything from the Rocky Mountains west is these terranes that arrived through this process of subduction and accretion over 280 million years and longer. Well, this is how it happens. This subducted mass, you have these island arcs, which is what the San Juans were. San Juan Island started out as undersea volcanoes 6,000 miles away at about the same distance as Taiwan, but way down south, at about the same latitude as Baja California. And over time they moved and they pushed everything in front of them, and it kind of masses up, right? And eventually it sutures on to that North American plate. Our story starts in earnest about 200 million years ago. So where you see MYA, million years ago, or MY, million years. A little bit more kind of setting the stage for what we're talking about. We're talking about the middle of the Jurassic period, right? So when dinosaurs came along, about 230 million years ago. That's the time period we're talking about. And it took this long for all of that stuff to happen. Wherever you see that star, that's where the San Juan Islands are today. So you can kind of see what we've got going on here at 200 million years ago. Let me kind of explain. What you see is South America and Africa are still joined. If you look at a map today, you can see that hump, right, where they were once joined. What we can also see is really interesting. This red line is where North America started 200 million years ago, and this is where it is today. So you get an idea of how far south it has moved in that period of time. We have things going on like this huge sand, not really a sand dune, a sand plain, a huge sand plain. So think of the biggest sandbox you've ever seen, or the biggest place with sand that you've ever seen. Stretch that over 4 states and you get an idea of how big this actually was. This is the late Triassic period. So Pangea has broken away and is beginning to flow south-southwest. The Pacific plate is moving north-northeast. Things are starting to happen. Things are starting to break apart here. Here you can see the first terrain that arrived. I've put it in context. So at about 200 million years ago, the 2 plates struck, some of it accreted, the rest of it subducted, and as it accreted, it also slid north. This is the Columbia Mountains in British Columbia and eastern Washington and Idaho. All of those arrived as an undersea seamound about 200 million years ago, saddled up to the coast of North America as an accreted landmass, and then slid north. Here we are at 170 million years ago. You can see lots of stuff happening again. So we have the Caribbean is starting to open up. We still have the connection through the Isthmus of Panama, right? But Africa is beginning to move away. This is the Middle Jurassic period. As it moves in this direction, we have 2 things happening. This is moving this way. That's the Pacific plate moving north-northeast, and the North American plate moving north-northwest. And then you have things like this happening, where it's actually turning. This is why we have such complex geology in the Pacific Northwest, because you don't only have the subduction and accretion, you also have land masses that are actually twisting and turning. The islands, the San Juan Islands, are a result of all that. Incredibly complex geology.
What's the land mass out there at the bottom of the left-hand red arrow?
This, that would become the...
One out in the ocean.
This one here?
Nope.
Oh, this is the San Juan Islands about to arrive in about 100...
The stars where they're at now.
Exactly.
Them.
Exactly. Yeah, they're on the way right now, right? So they are en route. They have not yet arrived. This is Vancouver Island. It's already arrived. This is actually called Rangelia. If you've ever heard of Wrangell St. Elias National Park in Alaska, named after the same person, right? So this guy arrived, saddled up to North America, began twisting and turning, and eventually it will do this. Today, the southern extremis of that, Rangelia, is Victoria, British Columbia, and it doesn't end until the Yukon. So one of the largest accreted land masses on the planet. Welcome Vancouver Island to the neighborhood. So I don't know why that's covered up there. So I put two of these here so you can see 90 million years difference between the two, the movement of Rangelia or Vancouver Island. Here you can see it starting to move this way. We saw it in the other picture, right? Starting to move this way. We've already got this terrain that's already arrived, this intermontane terrain. And then 90 million years later, it's arrived, it's sutured itself to North America. It's now part of the North American continent. What are these guys? It's the Cascades, right? The Cascades and the North Cascades. 150 to 130 million years ago, the Farallon plate was the first major plate geologically that mattered to North America. There were many others before, but the Farallon plate started all of this. The Farallon plate dragged Rangelia to a position off of the southern coast of British Columbia, and the Juan de Fuca plate now takes over. That's the one that's acting on us now, on the Pacific Northwest now. It's subducting at about 1.4 inches per year under that North America plate. And as it's happening, it's not linear, meaning sometimes that landmass will go underwater, sometimes it will come up, sometimes it will twist, sometimes it will even move away and then move back in. And this is all because of there are multiple forces going on here. I'll show you a diagram in just a little bit. And what you will see on the Pacific Northwest, with Seattle in the middle of it, is you have forces moving this way, you have forces moving from the Pacific this way, you have forces moving this way, and guess who's in the middle of it? Seattle. Seattle is right in the middle of that, and that's why this is such a dangerous place geologically. And I talk a little bit about that later. Not my information, I'll be giving you information about that risk from the Seattle Emergency Management Authority. So, 94 million years ago, this big seaway opens. Big seaway opens right here. All of that stuff, when you go to the Grand Canyon and Arches National Park and all those are a result of that big inland ocean that opened up about 94 million years ago. What happens when you have a sea open? Starts getting populated with sea life, right? So all that sea life begins to evolve in that inland ocean coming from the Pacific and elsewhere. And as it dies, it falls to the bottom of the ocean and over millions of years piles up, piles up, piles up. And then under heat and pressure, it becomes rock, sedimentary rock. So there's one piece that will play an important role as we go forward. Igneous rock is also important. Igneous rock forms all of the Cascades. That's all granite, almost all granite. Igneous rock means it simply started out as magma and lava and then cooled very, very slowly. And then you have metamorphic rock. It could start out as either one of those, and under heat and pressure, it changes its chemical composition, changes into some different kind of rock. And we'll look at that a bit later as well. So, 94 million years ago, you can see the progression of Rangelia. I put this in here just so you can get an idea of the progression. All the blue stuff is happening at the same time, the red stuff is happening at the same time, and the green. But you can see Rangelia as it progressed and finally ends up here. Strikes North America. It's kind of like a car collision. Think of these as massive car collisions. So when Rangelia struck, it struck with such force it couldn't subduct. Remember, it's too light to go underneath the plate, so it faulted, it slip faulted north. All of this stuff is getting pushed from behind in a process called thrust faulting. Again, the car analogy. If three cars are moving down a highway at high speed, one stops, the second one hits and rides up over it and pushes forward. The third one strikes the second one, rides up over it, and pushes them forward. This is how the San Juan Islands arrive, through this process called thrust faulting, getting pushed from behind in these minor collisions. But when they strike an object, it's just like that car, if the object that is strike is heavier and denser, that force has to go somewhere. So either that car is going to get crushed, it's going to slide to the side, or it's going to go underneath or up over. By 55 million years ago, almost all of the Pacific Northwest is in place except for the Olympic Mountains. So you see, we've got Vancouver Island here, we've got the San Juans. The only thing that's missing is the Olympic Peninsula, right? They have not arrived. At 55 million years ago, they're still not here. Pretty cool, right? So the continental margin was now west of the Cascades. Before that, the Cascades were still underwater. They hadn't risen yet, right? They had not risen. They rose through that plutonic, what I was talking about earlier, plutons, these massive bubbles of magma underneath the crust that bubble up and push up. And as they push up, that's one way that mountains are built. Another way that mountains are built are the way the Olympics got built. They struck and everything was about equal, so they began to rise. The granite of the Sierra Nevada at this time had formed, but had not yet begun to rise. So when you think of Yosemite National Park, I used to work there, I used to work in Yellowstone. Those are really, really simple geologic problems, right? Yosemite is a 400-mile long, 80-mile wide block of granite, right? That formed deep in the Earth's crust. And it cooled very, very slowly. Because it cooled very, very slowly, it became very hard, it crystallized, and then you have that typical granite look, right? Quartz and feldspar and very, very hard rock. But it also erodes very, very slowly. So by the time it came up and began eroding, it takes a very long time for it to erode. The Yellowstone National Park, I know, is no more than 260 million years old, because that was the last major eruption at Yellowstone. Just as an aside, you guys remember Mount St. Helens, right? 1980, 81? So Mount St. Helens, so just a comparative, talking about the size of the forces that we're talking about. When Mount St. Helens went off, it produced 0.25 inches of ash, right? The volcano, the last one that went off, one of the smallest ones, produced up to 6 feet of ash from here all the way to the Mississippi River. Those are the kind of forces that we're talking about, the size of the forces that we're talking about. So by 50 million years ago, the Olympics were still west of their current position. Out here, we can see a time slice from 190 million years ago. The Olympics and the San Juans are still off the coast. We talked about that earlier. But you're getting a picture of what's about to happen. By the same processes that the islands got here, now that Pacific plate is pushing, and as it pushes, there's lots of material just off the coast. This case, it's all sandstone, siltstone, mudstone. So this is sedimentary rock that's very, very light and very fragile, right? So as it got pushed from behind, it got pushed up and folded. Some of the thickest basalt in the world is in the Olympic Mountains. Basalt is what's formed when lava reaches the surface. So basalt is the Hawaiian Islands. So that's where these islands actually started. And then it continued to get pushed. And at some point in time, the forces are equal. The North American plate is too hard for it to push up against, or it can't dive under because it's too light. So it does this. And those guys began to rise at about 35 million years ago. They're still rising, by the way. And that's why when you go to the Olympics, so some comparatives here. When you go to the Olympic mountains, what do you see? You see really tall mountains with really sharp edges, right? And really pointy. That's indicative of a mountain range that is very young, right? It hasn't had time to erode. On the East Coast, where I grew up, the Appalachians were once prospectively as high as the Himalayas. But tens of millions of years, that erosion has taken those down. The highest point in the Smoky Mountains is 6,200 feet as compared to where they were, 29 or 30,000 feet, some 500 million years ago. And the same thing is going to happen to the Olympics. The Cascades, on the other hand, right? Most of them are kind of smooth, right? You're starting to see some of that erosion. And then you talk about, excuse me, then we look at Vancouver's Island, and it's indicative of a very old landmass that's heavily eroded as well. My point is, you can tell the age of a lot of the mountains by how much vegetative mass is on top of it, how much organic matter has collected, and what kind of trees and plants can grow on it. The more trees and plants, obviously, the longer it has been eroding, the longer it's been there. At 35 million years ago, volcanics in the Cascades begin. This is what we call the Cascadia subduction zone, or the Cascadia volcanic arc. All of those red triangles are volcanoes. There's something interesting about how those volcanoes got created, and it's tied to this thing of subduction and accretion. So when two land masses strike, one subducts, it begins to generate heat, right? It begins to generate heat by friction. And as it dives, it collects more and more heat. Down there, it's a lot warmer, right? So it's easier to collect heat, and there's nowhere for it to go. But as it drags down, it's also pulling in massive amounts of seawater with it. And what does seawater do when it's heated? It creates steam. What does steam do? Superheats that rock. But there's a third element that plays into this as well. Have you ever heard of serpentine or olivine? Anybody heard of those rocks? They're called greenstone, right? Thank you very much. It's called greenstone. It has some unusual properties. Under heat and pressure, it creates an exothermic reaction. So it's kind of like in chemistry class, we took magnesium, a little piece of it, and you throw it in a tub of water, and it explodes. Well, that's what's happening deep, about 20 miles deep in this subduction zone. Notice how uniform that is. It's all about the same distance from the coast, because that's about how far it takes to get 20 miles deep. At about 20 miles deep, all of this activity begins to happen. So you have rock at this point. Before it starts superheating, it's plastic. It's not really liquid. It's kind of like Play-Doh. You can move it around, you can mold it, but that's about it. When the steam reaches it, it begins to get more plastic, kind of sticks to your fingers. When that greenstone creates its exothermic reaction, it superheats it and it becomes liquid. And what do liquids do when they're superheated under pressure? They release gas. And what does that gas want to do? It wants to escape, right? It's got a natural escape zone. This is an old crack. All right? As these plate boundaries come into collision, those cracks in Earth's surface don't go away. They're still there. So when that rock at 20 miles deep and about where you see those volcanoes, when it gets down there, heat and pressure, the steam superheats it. It begins to get a little more plasticky. And then the greenstone takes over, superheats that rock. That gas wants to rise. It comes up through that crack in the earth, and we have volcanoes. About 35 million years ago, those volcanoes began going off, and they all the way down to Northern California, and they were erupting every single day for millions and millions of years. And what's the most powerful force in the universe? Gravity, right? Everything is ruled by gravity. So when that lava comes up, it has to come down. And it comes right down the west coast, or the west side of the Cascades, flows right in this direction. So all this geology out in here, it's already a mess. It started out as igneous rock in the middle of the Pacific. By the time it gets here, it's folded, it's twisted, and it's metamorphosized. It's changed its chemical composition. It becomes a different rock, shale, gneiss, schist. These are very fragile rocks, indicating how old they are and how much chemical change that they've gone through. So when the lava begins to cover that, it makes it even messier. It's even more and more complex. Fortunately, that stuff erodes relatively quickly. So at 35 million years ago, those volcanoes begin in earnest. I put this picture up here so you can see the progression. The blue is the older. Where you see blue and purple, that was their first location. Over roughly 30 million years, those volcanoes, that volcanic activity has moved to the east. Why has it moved to the east? Because that subduction continues to push deeper and deeper under the North American plate and continues to push to the east. So you get those volcanoes that are actually moving further and further to the east. 35 million years ago, this is kind of how the geology laid out. The major coastal range, that's the Olympic Peninsula, that's Vancouver Island, etc. South Cascades, the North Cascades, obviously we know about those. The Columbia Basin and the Okanagan Highlands have all been laid out at that point in time. We have these guys. Remember we talked about how sharp those edges are on that rock, on those rocks. Relatively young rock. Over time, it begins to erode. We start to see it getting a little bit flatter. And then something happened during that erosive period after the volcanoes stopped. Something happened that happens about every 41,000 years in Earth's history. Everybody knows the Earth is tilted on something of on its axis just a little bit, right? About every 41,000 years, the Earth tilts just a little bit further away. And when it does, it's called a Minkowitz cycle. These Minkowitz cycles are driving what's happening with ice ages throughout the history of the planet. Ice ages showed up almost as soon as the Earth cooled, and we've had many, many, many in Earth's history. Here you can see where the last one, this Cordilleran ice sheet, is moving from British Columbia and is moving south. On the island, you can actually see where those glaciers moved. We'll show more of that in just a little bit. This is the Minkowitz cycle. So when the Earth tilts just a little bit further from the sun, the North American continent is not getting quite as much sunshine. So that rain that was falling in the Pacific Northwest in British Columbia starts falling as snow, right? And as it starts falling as snow, it's colder, right? So that snow begins to accumulate every single day for millions and millions of years. At the bottom of that snowpack, it becomes ice. At between 175 and 205 feet deep, it has enough mass to begin flowing on its own. Gravity takes over and it begins flowing downhill. This is how glaciers are created, right? Glaciers are created because of that tilt away from the sun, the cooling of that particular landmass, and the precipitation that's now falling as snow. It was eroding, right? Now it's just piling up in the Cascades and in the Columbia Mountains up north. The glaciers have left us with a lot of cool stuff. Glacial till, sediment that define much of the region. Glacial erratics. If you've seen like odd rocks, you see them a lot on the islands, but you see these huge granite rocks. They're always granite. Anybody wonder why they're always granite here? They're granite because they were brought from British Columbia and northern Canada, right? They were brought by glaciers. At the height of the glaciation, about 18,000 years ago, 2.5 million years ago, the glaciers here were about 6,000 feet deep, more than a mile deep. So imagine standing on San Juan Island, looking to the north, you see a block of ice, a mile high, moving at you at 3 feet per day. That's what was happening, right? So a couple of things glaciers do when they move. Number one, they're pressing down. How many people have a memory foam mattress, right? Got a memory foam mattress at home. When you lean on that mattress and then you let it go, you can see it rise, right? Same thing happens with glaciers. So when the glaciers begin to melt, we're not only releasing fresh water, we're also relieving pressure. Remember, these land masses are floating on magma, on liquid rock or relatively liquid rock. So when we take pressure off of them, they rise. It's called hydrostatic rebound. And I'll show you a picture in just a little bit, the effects of that hydrostatic rebound. So we have a variety of old rock types, lots of mixed up stuff, lots of messy rocks here, covered with lots of strange geology like lava. Lots of convergent fault lines. When I show you a picture or a map of where the fault zones are in this region, it'll kind of blow your mind. A relatively unstable geologic region. I wouldn't encourage you to sell your houses now, but you might want to talk to your children and grandchildren. And the rain shadow effect from the Olympics all play into the geology, what's going on in the San Juan Islands. How many of you, do you guys know about the rain shadow effect and how dramatically it affects weather on San Juan Island? So much so that I can stand at American Camp where the wind is coming straight across the sound, right? So that weather hits the west side of the Olympics, got tons of moisture in it, rushes up the side of the Olympics, gets really cold really fast, drops all of its moisture on the west side, the Hoh rainforest, right? By the time it gets to the top of the Olympics, it's really cold, and it rushes down the side of the Olympics and straight across the Puget Sound. There's nothing to stop it. When you're at English or at American Camp in the wintertime, 60, 70 mile an hour winds are not unusual, and it's very dry air. I go 13 miles north to English Camp, I get 10 inches more rain per year, and I don't have any of that wind. And I'll have blue skies in the morning at English Camp, and it'll be completely fogged in at American Camp. So that's how dramatic it is in just, that 13-mile section. So that glaciation created those dry prairies, fertile valleys, and the salmon banks. So the prairies that we have on San Juan Island are some of the best preserved prairies in North America. And they're all there because of the glaciers. When the glaciers receded, they left all that material behind them. Think of a bulldozer. Think of a glacier as a bulldozer. It's moving along at 3 feet per day, and then one day, the Minkowitz cycle stops, and the Earth tilts back. And all of that moisture that was falling as snow is now falling as rain. It's warmer, so that glacier begins to melt. As the glacier melts, it's releasing huge amounts of fresh water into the Puget Sound that the Puget Sound is filling. It's, at this point, you have big sand regions of sandbars and flat plains where the wind is just taking that material and whipping it all across the region. As it begins to fill in, you see the Puget Sound begin to rise. You see it pushing down into Tacoma and the lower parts of the Puget Sound. You see the coastal areas in the islands and on the mainland beginning to disappear. All of this is from that fresh water coming into the Puget Sound. But it also leaves behind sand and gravel. Sand and gravel are very porous, does not hold water very well. So when that rain falls, it goes straight through. What grows well where there's not much water? Grasses, prairie grasses. We have these beautiful short grass prairies on the island, and they're not going anywhere because that wind coming across the Olympics, what moisture there is wicking that moisture out of the ground, and it doesn't hold water anyway, so only those grasses will survive there. So we have these beautiful prairies. We have this rich glacial soil. San Juan Valley in the middle of the island is one of the richest farming places in the Pacific Northwest. It's because it's all glacial. I mean, it's all leftover material that decayed and is now really easy to farm. It's loamy. And if we have any farmers in here, you know that loamy soil is what you want. And you have that in San Juan Valley. Not on the south end of the island, great place to grow potatoes, but not a great place to grow lots of other things. This is what I was talking about. When the glacier under pressure, that ice under pressure is moving across the land, it's taking up everything in front of it. If it can be broken off or dislodged, 6,000 feet of ice is probably going to do it, right? So it leaves that gravel and those rocks underneath it. And it's kind of like if I took a piece of sandpaper and pushed it across your nice dining room table at home, right? It's going to leave those striations. That's exactly what happened here. I can tell the direction where the glaciers moved on San Juan, and they all moved in the same direction from north to south. And these are at places on the island, high places on the island, in particular Young Hill. You can see a lot of them, some of them at the Mitchell Hill complex, etc. So it tends to smooth out everything under it. Valleys that were steep, river valleys, right? You have these in the mainland, on the mainland here, you have these river valleys, which are really steep, right? When glaciers move through there, it'll move down those same river valleys, but it'll break off everything around it, and you end up with these U-shaped valleys. When you see a U-shaped valley, that's indicative of glaciation. When you see these V-shaped valleys, that's indicative of erosion caused by the movement of water. Most of the erosion that occurred here and on the islands did not occur because of the glaciers themselves. It occurred in these post-glacial periods and these interglacial periods. Water is more erosive than that ice. So when the glaciers are melting and water is falling, that material that had been picked up by the glaciers is washed out into the Puget Sound, right? Every single day. This is what I was talking about. This is a cross-section. This is a picture from the American Camp Prairie towards the south end of the island. This is called Mount Finlayson. It's really not a mountain, right? It's only 230 feet high. What it is, it's called a terminal moraine. When that glacier moved and picked up all that material, just like a bulldozer, when it stopped and began to recede, it leaves all this behind it. That's a big sand pile. Nothing but gravel and rock. And there are a couple of interesting things about it. Number one, you see these terraces, right? There's at least 3. These are all over the island. This one you just can happen to see best. This is the effect of that hydrostatic rebound and fresh water going into the Puget Sound. Pressure is relieved on the islands, they begin to rise. Fresh water is coming up in the Puget Sound, it begins to rise. So they're doing this, and all during that period, tides are coming in and striking the side of that. These are old beaches, these are old tide lines. Pretty cool. And you can see the wind that's striking this. Otherwise, see, the trees are growing over there. Why aren't they growing over here? Same soil, same temperature. Remember, this stuff doesn't hold water very well. And when the weather comes across the Puget Sound, really striking winds, the moisture that is in that soil gets wicked away. Just like when you go outside and your t-shirt is wet and the wind is blowing really hard and it takes that moisture out of your t-shirt pretty quickly. It's what's happening here. By the time it reaches the top, it goes up and over. So you have this, the conifer forest on the other side of Mount Finlayson is able to hold its moisture. So you have this really abrupt transition zone. You see the same kind of thing in Great Sand Dunes National Park and elsewhere. We have these sand dunes down here, which you can't see very well, kind of up in here. Those sand dunes are there and not over here in the prairie because of the way the wind moves. The wind comes across the Puget Sound, gets up to Mount Finlayson. That sand that it's picked up can't go up and over, it's too heavy, so it sits there and churns. And that's how you get these beautiful sand dunes. Great Sand Dunes National Park is probably the best example of that. If I come literally 200 yards to the north, that's prairie and it's not sand dune because it's flat and the wind blows the sand and the material that it collects up and over and into Griffin Bay. Pretty interesting. Down here, these are called the salmon banks. These are really cool.
Is that photo facing north or south?
That's facing south, due south. So as Mount Finlayson eroded, it was much, much higher. But remember, it's sand and gravel. That stuff washes away really quickly, right? So as water falls on it, that sand and gravel is getting washed away. How many of you have been down to South Beach on San Juan Island? Yeah? So you know those bluffs that we have, right? Really precipitous bluffs, right? So those are their own ecosystem. For those of you that don't know, San Juan Island National Historical Park, if you stand on Pickett's Lane, within a 2-mile circle, you have 5 distinct ecosystems. It's really, really rare. We have the glacial dunes, we have prairie, we have conifer forest, we have lagoons, and we have these coastal bluffs. And if we throw in from the north part of the island, these really strange places called Gary Oak Woodlands, it's an absolute incredible place from a flora and fauna perspective. At any rate, as the rains fall on Mount Finlayson, again, gravity takes over and washes that material downhill, and it washes it right out into the Puget Sound. I'm going to lay the landscape here before I talk about the fishing, but the winds and tides are coming from this direction, so it's blowing everything back on land. We also have tidal activity in here. This is 300 to 450 feet deep through Cattle Pass, very deep, and the tides are moving in this direction. So what's happening is that material that's being eroded off of Mount Finlayson is trapped. It can't go anywhere. So it just sits there and collects. At low tide, that's between 6 and 12 feet deep. If I go 10 miles north to Limekiln Lighthouse, it's 600 feet deep. So you get that really abrupt transition over a 10-mile period, or a 10-mile expanse. Now, why that's so important to the salmon banks, why they're called the salmon banks. Geology is a really cool thing. It not only affects weather, right? It affects what kinds of plants grow there. Because of the kinds of plants that grow there, it determines what kind of animals are there that can feed off of those plants, birds, mammals, reptiles, insects, etc. So geology is determining what lives there, what happens there. Well, it works really, really well here in the salmon banks. Traditionally, the salmon banks are the most populated salmon fishing place in the Puget Sound, and it's because of this salmon bank. As the salmon traverse the west side of the island, north and south, salmon, as you fishermen know, have an unusual proclivity. They don't like to turn around much. They're kind of like geese, and they'll go in one direction. Well, the orcas take advantage of that. As they come out of that really deep water 10 miles north and come right down the coast of the west side of the island, they begin to rise, right? The salmon in big schools are coming up before they know it. The orcas take advantage of that. They're pack hunters. Some of them will get out in the sound and push those salmon towards shore, while the others are down here feeding in these really shallow waters, right? The Hudson Bay Company then took advantage of that as the Native Americans did. Native Americans fish there, catch 100 fish per day. It's all good. Hudson Bay Company took over 500 fish per day. Americans arrived and we applied steam power to the problem, and in one day in 1917, at one fish trap along this stretch of beach, there were 12 fish traps here. On one day in 1917, one trap took in 250,000 salmon. They did this for 50 years, every summer. So much so that by 1934, the state of Washington outlawed fish wheels and these particular kind of salmon traps, because they saw it was already decimating the Puget Sound. There was some politics involved with the purse seiners as well, but we had created a problem in 1934 that we're still trying to get over today. At any rate, geology created all of this. This is all an effect of geology. So that tectonic activity has left its mark. We're primarily metamorphic and sedimentary rock. There's no natural granite on the island, although I have a debate with a friend on the island who's a geologist. He says he's found some up on the north end of the island. He can never make time to go show me. So I don't know if it's really there or not. It may or may not be. But you have this really small section up on the north end of the island. We got this place called Limestone or Limekiln Point, right? All these limestone mines on the west side of the island. It's only a really small stretch. It's only like a 6 or 7 mile long stretch where that limestone is at, and it was heavily mined. But as you can see, beginning with the parent rock, over time, so that yellow area, or that yellow arrow, is indicating how that rock metamorphosizes or changes to a different kind of rock. So it starts out as granite. Heat and pressure and time, it becomes shale, slate, phyllite, schist, gneiss, and it begins the rock cycle again. So you remember how the Olympics, what kind of rock the Olympics are: sandstone, mudstone, siltstone. So it's all sedimentary rock. It's relatively light rock anyway. But as rock gets subducted, whatever kind of rock that is, it gets melted and it comes out as volcanoes somewhere else and becomes igneous rock. This is called the rock cycle. So this is happening all over the planet. Rocks, the only rocks that were relatively certain on the planet that are the original rocks after the Earth cooled are in Australia, New Zealand, and then up in the Arctic Circle, the Hudson Bay area. Apart from that, almost all of it is recycled rock. Something that started out as one kind of rock, subducted, got melted, and then got either pushed up or brought up as lava. This is that geologic cross-section of the island. So you can see, so we're going north to south. Johns Island, Spiden, we got down to Rosario Straits, we got San Juan Island, and then we get all the way down to the lower islands. Whidbey would be further south. That thrust faulting, getting pushed from behind, is what we see here. Those layers getting folded over millions of years, getting stacked on top of one another. But not only getting stacked on top of one another, they're going down and they're getting pushed from behind, and then they're coming back up. And they're getting twisted sideways. So all of that rock is not moving in a straight line. It depends on what pressures, what forces are acting against it. We have lots of different kinds of metamorphic rock on the islands. We've got the Haro thrust, the Orca thrust, the Rosario and Lopez thrust, and all these are different kinds of rock from the Turtleback complex. These are designation given by geology to define the rock types that are in these different places. This is Dead Man's Bay on San Juan. If you go there, it's really cool. Just south of Limekiln Point, you can go down to the beach and walk to the left, and you can see that old volcanic rock that started out 6,000 miles away in the Pacific Ocean. It's pretty cool to see. Then you see the Garrison Schist up on top of Young Hill. As I walk up, I can see it transition. I can see it becoming more and more metamorphosized. The Constitution Formation, Mount Constitution, right? So Orca's Chert and Dead Man Bay terrane. So all these are different rock types spread throughout the islands. There's not one specific rock type. A lot of times these are called exotic terranes. I think I mentioned that earlier, right? They're called exotic because the geology in them is different than the geology around them. The Olympics is all very light rock, all sedimentary rock. The islands are metamorphic rock primarily. The Cascades are almost all granite. Within a 60-mile circle, we have 3 completely different geologies, all stacked on top of one another, all having gotten here in a different way, all having been formed in a different way. We really do live in a special place. I'm sure you already know that, right? So these are some of the rocks we see on the island. You can see the twisting and turning here, right? This is Orca's Chert. Chert was highly prized by the indigenous people because it's very hard, but it's easily flaked. So they made spear points and knives out of this material by flaking it off. Here we see schist, very easily broken. you can see the facets or the planar joints. If I hit that with a rock, with a hammer, it would break apart pretty easily. When I take I do a geology walk on Saturdays in the summer, and I stop at this one place halfway up Young Hill, and I take a piece of that rock, and I say, "These are what your houses are built on. How comfortable do you feel about your foundation?" "Well, I feel pretty good. It's okay." And I throw it up against the side, and it shatters, and they go, "Oh my God, maybe I need to talk to my insurance agent." This is Garrison schist as well, not as metamorphosized. You can see these different rock types having different ages and not as highly metamorphosized depending on where you're at in the islands. And then of course sandstone. We talked about that rain shadow effect. I got ahead of myself, but this is a picture showing what that rain shadow effect is all about. It's going to get worse. It's going to be more dramatic. It's going to be more dramatic because the Olympics are continuing to rise. As they rise, it's going to make colder air. It's going to mean that a lot of that weather flows north and south instead of coming up over. Our weather on the islands is probably going to get drier, if it's not already dry enough as it is. And then you have things like this, Death Valley. Death Valley has the same kind of thing. The winds come into those valleys and push all that sand up to these mountains, and it can't go anywhere. They end up being these huge salt and sand flats. So, what does the future hold? This is a geologic stability map of North America. This is called the New Madryn Fault, right? We get earthquakes there, back east every once in a while, Missouri, Tennessee, Mississippi in there. But you can see what's happening here, right? That's because of that plate boundary, right? There's no plate boundary action here. Remember, all this is getting pushed from the Atlantic towards the Pacific. This is all really old geology over here. But beginning about right here, that's all stuff that's collected from the Pacific Ocean over hundreds of millions of years. And as it collects, it doesn't, it's got a lot more fault zones. It's still moving. It's not stable. It's going to be hundreds of millions of years before that becomes stable. The further it moves inland, the more green and blue it's going to get. But right now, this is a very unstable area geologically. This is us. This is Seattle. So the things that I want to draw your attention to is you can see all the major geologic components lined up here. We have the Pacific Plate moving from the south. You can see the arrows here, right? That's a Pacific Plate. You've heard of the San Andreas Fault? Pacific Plate sliding up the coast of North America. I love these disaster movies where the San Andreas Fault has California falling off into the Pacific Ocean. And it's not going to happen. If anything, it's going to get pushed more and more inland. It's going to rise up. That's how the Sierras were created in the first place. It's going to rise up, or it's going to slide north. If you come back in about 100 million years, I could be a ranger in Canada instead of Washington. Then we have the Juan de Fuca Plate. It's moving north-northeast, as it has been from its predecessor, the Farallon Plate, for hundreds of millions of years. We have the Vancouver Island, which is Rangelia, and all this material in Canada is moving southwest. And then I have all of this volcanic activity here, just behind us. And you see what's happening here. This rotating block that Seattle sits on, it's not only getting pressed from below, from the side, from the north, it's also rotating. Remember we talked about the islands getting twisted? And it all intercepts right here in downtown Seattle. It's actually called the Seattle Fault for a very particular reason. It runs right through downtown. Kind of crazy. These collective forces have driven most of the geology in the entire Pacific Northwest. Everybody here, wherever you live, has something special about their yard where they live that's affected by the geology that I've just described here. This is that fault zone. We talked about the fault zone map. These are all major faults. This is the Puget Sound. These are all major fault zones. This is a Cascadia subduction zone pushing this way. These are big faults, and there's lots and lots of them. And any of those could take over at any point in time. How many of you have been to Limekiln Lighthouse, the state park there? So, if you'll remember coming from the south, you get ready to go into the entrance, but nah, I'm going to turn right now. Go up the hill, yeah, and go up the hill and around. Has anybody ever looked up about 100 feet above you and seen the land up above you? No, never paid attention? Well, if next time you're there, do. As you go along that road that goes around behind Limekiln, if you look up, you see a 100-foot tall cliff. And people live up there, right? How did that cliff get there? Remember we talked about just off Limekiln Lighthouse, the water, it's why the orcas are there. It's why you can go to Limekiln Lighthouse and throw rocks out into 600 feet deep water. It's why the orcas come there, because it's really deep, right? They can play there, they can fish there. That's because that cliff there is because at some point in time, gravity took over that big deep trench right off of Limekiln Point. At some point in time, gravity started pulling in millions of years, and then all of a sudden it broke. And as it broke, it dropped and it slid into the Puget Sound. It's called a slough. You see them, there was a town, I think, called Orso that went through. Okay, so this is the exact same thing. The exact same thing happened, right? So you had, at the bottom of that town, there was some kind of activity there that made it weaker than everything above it. Water fell on it, soaked it, and at some point in time, that landmass just dropped and slid. Gravity took over. Well, that's what happened to Limekiln as well. That's why you have that big tall cliff there, because of one of these fault zones. And that kind of activity could happen anywhere in the islands, anywhere here. If you live close to a big rock cliff, that's where this stuff is going to happen most likely. This is from the earthquake planning scenario from the City of Seattle's Emergency Response Division. I didn't want to bring this and scare people. That's not my intention. I don't think there's anything to be afraid of at this particular moment in time. Although people are wisely planning for this, right? Because their words that I'm about to show you are pretty dramatic. This is the 2009 planning scenario associated with all that stuff that I just showed you. Those plates moving, all those fault zones, all that instability. You can see where it's at, right? Right through downtown Seattle and up to Everett. Not so much up in the islands, so I'm safe for at least for a while, but you guys are in the yellow over here, right? You guys are in the yellow. This is from them. Cascadia subduction zone earthquake would generate the most widespread damage of any scenario. So lots of scenarios here. We could have the Pacific plate moving north, pushing north. We could have the material from Canada moving south. We could have this rotation occur. But the most dangerous one is the Pacific plate subducting. Although the maximum intensity of shaking would be less than for a large shallow earthquake, such as on South Whidbey, Island Fault, Seattle Fault, or Tacoma Fault, strong ground shaking would be felt from northern California to northern Vancouver Island. In the fall 2012 Washington State Magazine is all of this information. You can go to the Seattle Emergency Response Team and get all this information for yourself. They actually have an app that you can get for your phone. You sign up and you get warnings for things like major geologic events, tidal waves, that kind of thing. 250 million years from now, everything that I've just been talking about is going to continue to happen. Nothing has changed. It's becoming more stable, right? And it will continue to become more stable over time. But all of this movement is going to continue to happen. It's cyclical. The old adage that the only constant is change is absolutely true with regard to geology. The plates are going to continue to move, subduct, and accrete. Volcanoes will continue to develop, activate, and go dormant. Sea level will continue to rise and fall. Ice ages and glacial periods will continue to cycle. And human beings will continue to be born and die. And it all begins again and again and again. So this is from James Hutton, that gentleman that discovered modern geology, plate tectonics, way back in the 1700s, and I think he absolutely nailed it, and he didn't know that he did. So I always end this talk by telling you a little bit about what geology did for me personally, and I mean this very sincerely. So I came from a business background. My life was very hectic. It was very, I was very goal-oriented and driven. When I quit, when I retired, my resting heart rate was 92. Today it's about 63. So this is what the parks have done for me personally. But it's done something else. As I started to study geology, I saw these vast expanses of time. I saw these forces that I asked a mathematician on one of my walks a couple of years ago. I said, "Can you help me understand the math involved in this?" He says, "I could, but you wouldn't understand it. The forces at play here are well beyond anything that anybody has reason to kind of factor." So we're talking about things that are way beyond anything that I can even imagine. And what that's done for me is I put it into a little caption for myself. The more I understand about the vastness of time and the universe, the more I understand my insignificance, and the more I appreciate the significance of the moment. That's what I'll leave you with. Understand geology. It has an effect on people. It fascinates us, but it helped calm me. It helped me find a center in my life. It's odd that geology would do that, and not something else, but I absolutely love it. Now, a couple of things for you guys you're now going to be motivated to go out there and read everything you can about geology, right? This is my favorite book. This is called Geology Underfoot in Western Washington by Tucker, and it does a really great job of explaining all of this in layman's terms, although there is some science in there, and there's a lot of other sites in there as well. It's kind of like roadside geology. It's got a lot of multiple vignettes across the state, so you can actually see different places that he has gone to and explored the geology there. You can go there and explore geology there for yourself. I invite you to come to the islands and explore the geology there. It's a pretty cool place. We'll do a field trip. Thank you very much.